All right, hello everyone. Welcome to my channel. This is a channel for educational purposes, and we usually look at late great theories of everything that have profoundly influenced my life, helped me out in various ways, and given me different perspectives, a new paradigm, and things that I'd like to spread out. Today is our 351st video that we've done on the reciprocal system of theory. And this is a system of theory that was originated by one Dewey B. Larson back in the 20th century. He died back in 1990, but not before he put out a dozen or more books and 50 or so articles, many talks and other ephemera on the reciprocal system. The basic gist of the reciprocal system is that we live in a universe that is made entirely out of motion. Not matter or energy, not force or anything else, but motion, and it's specifically what he calls scalar motion. This is a motion that has a magnitude, but it has no specific direction. And the model that you could use for visualizing scalar motion is to take a balloon with dots on it. When you blow up the balloon, all of the dots are moving away from each other, but they're not moving in any specific direction, or they're moving in all directions. So that's a scalar motion. You can also note that the people who operate the Hubble telescope discovered that all of the distant galaxies are moving away from each other. So this is an example of a real-world scalar motion, unless you are willing to, assume that our galaxy is at the center of this universe and it is not moving, then our galaxy is also participating in that motion. And you can also think of it in terms of a clock. The clock is always getting later and later and later, but in no specific direction. This is what Larson calls clock time. Clock time is a scalar motion in time. And it comes as a result of a kind of a faraway view of time. Now, for Larson, and then, the recession of the distant galaxies is really what Larson would call clock space, scalar motion in space. Now, when Larson uses this term scalar motion or motion, motion for Larson is the relationship between space and time. That sets up a reciprocal relationship between space and time, hence the name, the reciprocal system. System is based on this reciprocity between space and time. Space and time, as reciprocals, do not exist separately. They only exist together in motion. They have the same qualities, that scalar aspect being one of them, another being a three-dimensional aspect, what Larson calls coordinate space and coordinate time. We're accustomed to the idea of coordinate space, not so much with coordinate time, but by the reciprocal postulate, there is also a three-dimensional version of time. And then also space and time only come in discrete units. There's a minimum unit of space and a minimum unit of time. You have to have a full unit before you have either one of those things. And if you have exactly 1 unit of space in 1 unit of time, then you have the speed of light, or what Larson calls unit speed. 1 over 1 equals 1. And, time and space, basically motion is a fraction with time or space as the numerator and space or time as the denominator. So speed is one of the most basic motions that we can reckon, and speed is space over time. The bicycle is moving at 12 miles per hour. 12 miles of space in 1 hour of time, space over time. So to the speed of light is space over time, 1 unit of space in 1 unit of time. Now, those units are very small to make it up to your discrete unit, but space is 4.56 times 10 to the minus 8 meters, and time is 1.52 times 10 to the minus 16 seconds. And but 1 unit of space and 1 unit of time is the speed of light. And so in Larson's system, the speed of light is really like the background or the state of rest, the 0 point or the reference point. He calls it the progression of the natural reference system. The universe is always moving outward at the speed of light in all directions. Now, we are not able to always observe that, because we are in a gravitational field, which is the opposite motion of this progression. Gravitation is also a scalar motion, but it's an inward scalar motion. So you would just take your same balloon, and instead of blowing it up, you would suck it in. And all of the dots would be moving toward each other, and but there would be no specific direction. You would only get a direction once you arbitrarily decided that one of those dots is actually motionless. This is our reference point. And then once you decided that one of the dots is motionless, then you can determine the directions of the other dots. So the direction is an artifact of the reference system, not of the motion itself. And so these concepts of like a force field in gravity, between two different bodies is fiction in reality, and it doesn't come about until there is a reference point that has been determined, which has nothing to do with the motion, but has just to do with your choice of a reference point. Motion is a fraction with time or space as the numerator, space or time as the denominator. You can have time over space, that would be energy. It took me 1 hour to push that thing half a mile. Time over space. Matter, turns out, is time to the third power over space to the third power. Acceleration, space over time to the second power. I dropped the ball out the window. It fell at 32 feet per second squared. 32 feet of space in 1 second squared of time. Space over time squared. Force is the conjugate of that, time over space to the second power. And all of our basic scientific quantities are relationships between space and time. They are all motions. So again, where you have Larson's, the speed of light is the background motion of the universe, That makes sense because in a universe of motion, the first thing that you have is motion. Um, and you do not need to have a thing before you have the motion. The motion itself, the thing is actually also just a motion. So the motion comes before the thing that's moving. And you have to be able to at least accept that, even if you maybe don't understand it or if it seems absurd to you. You have to be able to accept that for the time being before you can even pretend to think about studying the reciprocal system. That's just a part of it, that motion comes before the thing that's moving. And the thing that's moving is motion in and of itself. Now, if we have this speed of light boundary, it's a boundary between two different sectors of the universe. The speed of light is the boundary. That means that half of the universe is moving faster than the speed of light. This goes against all of the legacy science, especially Einstein's dictum that the speed of light is the maximum speed of the universe. Therefore, he has no idea about this, what Larson calls the cosmic sector, where all speed is moving faster than the speed of light. And then there's the material sector that we're more familiar with and that Einstein was comfortable with. That is where the speed is less than the speed of light. Now, fortunately, because of the reciprocal system, we can tell that what's going on in the cosmic sector, though we may not be able to observe it directly, and it's a little bit opaque to our understanding, what goes on in the cosmic sector is exactly the same, generally, as what is going on in the material sector, because they are reciprocals of one another. All you have to do is invert the relations of space and time. So, for example, in the material sector, you have coordinate space, 3 dimensions of space, and you have clock time. The clock is always getting later and later and later. And we're comfortable with those two relations in general. But then in the cosmic sector, we have coordinate time, 3 dimensions of time, and clock space. The clock is, space is getting farther and farther and farther apart. So those are relatively unfamiliar relations, but those that gives you a picture of what's going on in the cosmic sector. In the material sector, you have matter, and in the cosmic sector, you have cosmic matter, what Larson refers to as cosmic matter, what legacy science refers to as antimatter. And this matter is generally formed within a second set of boundaries in the reciprocal system, and that is due to the discrete unit postulate. If you don't have a full unit of space, then you don't have space. So that dictates that within the material sector, there is a small subsector of that sector where you are dealing with less than one full unit of space. If you don't have a full unit of space, then you don't have space. And if you don't have space, then you only have time. And so Larson refers to this as the time region. And in the time region, the relationships are again inverted. And this is the realm of microscopic phenomena, such as atoms and molecules. And so too over in the cosmic sector, except having to do with time. If you have less than 1 unit of time, then you don't have time. And if you don't have time, then you only have space. And if you only have space, then it's what Larson calls the space region. And this is what you would refer to as, not microscopic, but maybe instantaneous, or from very, very short lengths of time, and not enough to make a full unit. And within that realm, again, the relations invert, and you have the realm of cosmic atoms and cosmic molecules. Now, today we're going to be looking at and trying to finish this paper called Quantum Pi, that was written by Dr. Bruce Peret, who is one of Larson's chief followers and revisers, especially after Larson died in 1990. Peret himself died back in 2020, but did some fantastic work along with Dr. KVK Nehru, putting together what they call RS2, which is the re-evaluation of the reciprocal system, kind of updating it, modernizing it, and kind of just getting some of the kinks out of the system, along with being still within the spirit of the reciprocal system. And this article, Quantum Pi, is the 5th article in his RS2-105 series, 101, 102, 103. This is number 105. And we started this article 2 days ago. So if you want to start at the beginning, go back a couple days in the archives. We are at a section right now that's called acceleration and orbital velocity. Now, just just to refresh your memory, Quantum Pi is basically saying that, looking at this other guy, Miles Mathis, and his work, and he was saying that pi equals 4, not 3.1415925, because pi is measured in a square, not a circle. Pi is the relationship between the circumference and the diameter. But with a square, the relationship between the circumference and the diameter is 4. But if you're dealing with discrete units, you ultimately, once you get smaller and smaller and smaller, you're dealing with something that is a square. It only becomes circular when those units become large. And Peret is using the analogy of pixels on a screen. You could also use an analogy of a cartoon, where you're not seeing exactly what's going on. When you see pixels on a screen, you can see a big circle, but if you look at it really close, it is actually jagged, like a stair step. The lines are straight, but they're so small that it looks like it's curved. And that's the case with the universe, if it follows this discrete unit postulate. And it's the same with the cartoon. What we see is a continuous progression, but if you really broke down the universe into single units of time, which is 1.52 times 10 to the minus 16 seconds, which is 6.576 quadrillion units per second. What you would see is one frame at a time, one still frame at a time, just like a cartoon. You see one picture, and then another picture that looks very much like the first one, but there's a slight change, and then another one that looks very much like the one before, but a slight change. And then when you look at them all in a sequence, it looks like there's just continuous motion, but there isn't. It's discrete. And so Larson, Peret here is really saying pi ultimately does equal 4 when you break it down, but and it never equals 3.14159.265 blah 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 exactly. That is the ideal value if you ever got to infinity, but you can never get to infinity, so pi is just approaching. It only can approach that value. Okay, so we're going to start reading acceleration and orbital velocity. In a universe of motion, everything is based on the ratio of motion being speed s over t or energy t over s. There are no unitless constants such as pi. So what are the units of pi? We normally represent the calculation of speed as distance per unit of time, v equals s over t. That would be velocity. But I guess he's using velocity because it begins with a v instead of an s. Anyway, where s is a spatial distance. This can also be expressed as an acceleration for a quantity of time, v equals a t, or in natural units of space and time, space over time equals space over time to the second power times time. But going around the circumference of a circle is not the same thing as moving in a straight line, which is what these equations represent. Circular motion is referred to as an orbital velocity, or v to the second power. If we treat our equation for circumference, c equals 2 pi r, as the equation for orbital speed, expressed in natural units of space and time, we get c equals 2 pi r, or s to the second power over t to the second power, equals s times t to the second power times s times c, circumference, which equals 2 pi r, or s to the second power times t to the second power, or over t to the second power, equals s over t to the second power times s, where the circumference is an orbital velocity, the radius is a spatial distance, and the value of 2 pi has units of acceleration. We can therefore define acceleration in 2 different ways. One, the linear velocity over time. Velocity over time. A equals vt, v over t, or s over t to the second power. Or 2, orbital velocity over space. A equals v to the second power over s, or s over t to the second power. Like its yin-yang counterpart, all motion in the reciprocal system is a relation of rotation, yin orbital velocity, to translation, yang linear velocity. In the material sector, rotation is in time and translation is in space. That's probably the most important thing I think that has been articulated here. In the material sector, rotation is in time and translation is in space. Both of these equations are natural consequences of the unit of motion concept. Consider that with pi equals 4, the equations become simpler, and we find that Larson is already using them, though he never realized that he was dealing simply with a pixelated perimeter and area. For example, the circumference is 2 pi r, or simply 8r. Circumference is an orbital velocity, and the radius is linear, a line. So this is defining the relationship between rotation and translation, which is found in all of Larson's 8-to-1 ratios concerning the electron. Further, if we look at the area equals pi r squared, or area equals 4 r squared, we find that this is exactly the same formula that Larson uses to compute the periodic table of the elements, 4n squared. At a conceptual level, the definition of pi equals 4. Oh, I'm sorry, that did say 4 pi squared. I'm sorry. At a conceptual level, the definition of pi equals 4 is stating that, I'm sorry, it does say 4n squared. I'm having trouble telling the difference between the pi and the n here. Okay. At a conceptual level, the definition of pi equals 4 is stating that in a discrete unit system, quantized, the electric rotation is analogous to the circumference, and the magnetic rotation is analogous to the area. This also explains Larson's choice of a one-dimensional rotation for electric motion and a two-dimensional or planar rotation for magnetic motion. This quantum pi relationship will be further expounded upon in following papers, demonstrating that they are the underlying structure to electron orbitals and the atomic structure as organized by the periodic table. The reciprocal system, being based solely on natural consequences, those found in nature, tends to use the quantum pi value of 4 in many applications. So pick your piece of pie by the reference system in use. Okay, that is the end of this article. I'm just looking at the footnotes here to see if there's anything that needs to be added. Doesn't look like it. So that's the end of RS2-105, Quantum Pi. Tomorrow we will be getting into RS2-106, which is called Dimensions and Displacements. And I think this one is pretty good. Thought-provoking. The Quantum Pi article lost me from time to time, but I do think that some of the relationships that he made there at the end are important. The electric motion is the one-dimensional. The magnetic motion is the two-dimensional, the disk or the plane. Okay, and then he also said something else that I thought was pretty important. That was in the material sector, rotation is in time and translation is in space. Now the reverse would be true in the cosmic sector. In the cosmic sector, the rotation would be in space and the translation or the straight motion would be in time. So that's also an important relationship there. So, you know, you can, it's just, you can think of time in terms of rotation, and that makes a lot of sense. You know, time is recurring. You can think of that in terms of music also, in terms of music theory. You know, that's the, you know, the double helix or whatever of music theory. As you go up in frequency, you know, you're going around in a circle, and so you end up coming back to the same note, but you're twice as high. So you're you know, when you, in music, when you go around the, you know, up the scale is the shape of a circle, well, a spiral, because you end up a little bit apart, but the octave is in the same place as the original note, and then the second octave is in the same place, so you're going around like that, and that has to do with frequency. So that is a measure in time. Anyway, we'll flesh that out more as we you know, cover those topics. But stay tuned for tomorrow for RS2-106, dimensions and displacements. Thanks for tuning in today. Have